astronomy. Let's get into Unit 9 here with space-time. So, follow along. Typically we'd be making these graphs, but I will do it for you and ask you some questions on our Unit 9 assignments about these graphs. You don't have to make any. So, with space-time graphs, right, you make an axis on the bottom that represents space, which would be like distance, like how far away something is from another thing, right? Then you'll make an axis across the vertical, like this, that, of course, you probably guessed it, represents time. Now, the key to a space-time diagram is that these two axes actually use the same units in a way. So if I'm going to use minutes for time, then I have to use a minute unit for space, which is a distance. So maybe some of the brighter ones of you are recognizing a time-sounding unit that represents distance, and that would be like a light second, a light minute, a light year. Those are actual distances, but they sound like times. So if I'm going to use minutes for time, I'm going to use light minutes for space. Okay? So now when I plot things on a space-time diagram, if I have an object here at some moment in space and time, and it doesn't move from side to side or forward, backwards, whatever, then that object would just simply travel through time. So you'd have something that looks like this. This would be an object that is not moving. Okay? Doesn't really matter where you start along the space axis because they're just locations in space. Okay? So let's pick another spot, and this will be the spot. And at this spot, this object is going to move. Okay? Let's call it a beam of light, which means a beam of light in 1 minute will be able to make it 1 light minute away. So in 1 minute of time, it's going to make it 1 light minute away. So after 1 minute, it's there. In 2 minutes, it will get to here, right? 2 minutes of time, it will have made it 2 light minutes. So something that moves on a 45-degree angle through the corner of every one of these boxes is pretty special. That means it's traveling at light speed. And nothing can go faster than that. I could travel the other direction at the speed of light. I would go this way, through the corners, through the corners, through the corners. But I could never go any way tipped more than that. Okay, it would have to be tipped the same or less. So I go from this extreme of going straight up, which is no movement, to faster and 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 faster until I get to there, right? And this area out here, actually, when I talk about in class, these are locations in space-time that do not exist. Because there is no record of them. You can't get information from those places. You can't give information to those places. So in our reality, those locations don't exist. Okay? If I'm here and I want to know information, something that's 1, 2, 3, 4 light minutes away in 1 minute of time, that position in space-time does not exist. There's no way to get information or give information faster than the speed of light. Okay? So we have a quick intro into space-time diagrams, right? Now the real meat and potatoes, we draw a couple of these in class, but the real meat and potatoes comes in Einstein. Okay, Einstein had started to concoct this weird reality that says that time is relative. Okay? I'm just making another space-time diagram sheet here. Okay, so there's space. And we'll have time going up. Einstein had this weird reality. He was sitting on a bench near a river. Right? So let's say here's the bench. Let's see if I can draw a bench. And we have Einstein sitting on this bench, right? And he was watching this boat. And it had this, he imagined this crow's nest up at the top with someone up on top. And that person up top maybe had an anchor. Okay? And then there was a captain of the boat down at the bottom. Okay? And he imagined, because this boat was sailing, what he would observe and what the captain would observe if this anchor were dropped. Okay? So let's imagine that this boat sails all the way across, and at this moment this guy up top drops the anchor, and over here at this moment the anchor hits the captain down at the bottom. Okay? So from Einstein's perspective from the side, what does that path look like? Okay? So from Einstein's perspective, this anchor follows this path. Right? From the captain's perspective, who assumes that the boat is just sitting still, it's in the boat, he looks up, the anchor's directly above his head. After time passes, the anchor's right next to him. So from the captain's perspective, the anchor took this path. All right? Now, what Einstein realized is if he was wearing a watch, that's a watch, and if the captain was wearing a watch, and they both started their watch the moment they saw the anchor let go, and they stopped it the moment the anchor hit the boat, their watches would agree. Watch time equals watch time. They both time the same event. So the time it takes to go from up there to down there has to be the same, right? But then he says, well, wait a minute. This path that I saw is way longer from my perspective. Yet it made it there in the same amount of time. So Einstein theorizes that time must have slowed from his perspective. Okay? Now, he doesn't have any way to prove this yet. It doesn't come until later. James Clerk Maxwell, okay? James Clerk Maxwell makes this weird discovery that says, if I'm in the back of a truck and I throw a ball, let's say I throw it 15 miles per hour, and this truck is moving 30 miles per hour. Okay? A person from the side watching this, you can see that I wrote it a little low, it's just a head looking, would see this ball move away from the truck at 15 and 30, the difference between those. So it'd actually see the ball moving 15 miles per hour this way. Okay? It'd have 30 miles per hour minus a 15, so 15 miles per hour this way. What if I turn around and I throw the ball 15 that way? An outside observer would see, it would see 15 plus 30. It would look like a 45 mile an hour ball being thrown. Okay? Because that would add those speeds. What James Clerk Maxwell realized with a few experiments, he realized that light does not behave that way. Okay? Light, and he did this, one experiment they did was, imagine this is the Earth. Okay? I got some countries here. This is the Earth. And he took a light and shined it one way on the rotation of the Earth with the rotation of the Earth, and realized that they measured 667,000 miles per second, I think it is, something like that. 670, I don't know. 300 million meters per second. And then he turned the flashlight around and measured it against the rotation of the Earth, and he got the exact same speed. Exactly. Didn't have any change if it was with the rotation of the Earth or the reverse. And it was this weird sort of realization that light has to be measured to be the exact same speed for everybody. Okay? So we got those two things working for us. So let's now take a look at a space-time diagram where I'm going to perform a little experiment. I'm going to have one person sit here and do nothing. Okay? This guy's going to do nothing, which means he's going to stand still. So his movement on a space-time diagram is exclusively time. Okay? Time passes. At the same moment, I'm going to take a red light and I'm going to shine it both directions at the moment we start the experiment. Now, what does red light look like shining on a space-time diagram? It's going to travel through the corner of every box. And typically for something like a light beam that's not a person, you put a dashed line. Okay? And it's going to go both directions. See if I can get this nice and straight. Alright, there goes my beam of light. So you'd think if everybody measures the speed of light to be the same, you'd think that after, say, 4 minutes, how about that? 1, 2, 3, 4. 4 minutes. Let's imagine 4 minutes go by. 1, 2, 3, 4, right here. And you ask this person here that was sitting still and say, how far away is that leading edge of light that was sent this way, which would effectively be saying how fast was it moving. If it's been 4 minutes, you'd expect it to be 4 light minutes away because it has to travel at the speed of light. So he looks off and he sees 1, 2, 3, 4 light minutes away that way. Perfect. Right? Then he looks this way at the other direction. 1, 2, 3, 4 minutes. Perfect. So a stationary observer perfectly complies with Maxwell that says this speed of light is the same in both directions. Now, what if at the same time I send someone to travel at half the speed of light? Let's have them go this way. What would half the speed of light look like? If this is the speed of light, something slower goes this way. Something traveling at half the speed of light would take 2 minutes to get 1 light minute away. It would take 4 minutes to get 2 light minutes away. And 6 minutes to get 3, and 8 minutes to get 4, right? So I have this weird sort of slope of 2 over 1. Okay, that's someone traveling half the speed of light. Half the speed of light. Now, after 4 minutes pass, you tell Mr. Green Pants here, this is green if you can't tell, you tell Mr. Green Pants to say, hey, Mr. Green Pants, check your watch. In 4 minutes, I want you to look both directions and tell me how far away that beam of light is. Right? Because according to Maxwell, you ought to get the exact same measurement, whether you're moving or not. Whether you're spinning with the Earth, spinning against it, light is always measured to be the same speed. So you ask Mr. Green Pants, all right, how far away is this one? And he says, oh, it's only 2 minutes. And he looks this way and he says, oh, it's 1, 2, 3, 4, 5, 6. 6 light minutes away. So you're telling me that light, which cannot go faster than light, got somehow 6 light minutes away in only 4 minutes of time? How is that possible? Okay? And it comes back to Einstein realizing that when an object's moving, this must distort time. Okay? So let's take a look at how we fix this. The way that we fix this is Mr. Green Pants, when he moves, his space axis does not stay horizontal. This horizontal line is perfect for non-moving objects like the blue guy here. But the green guy, as soon as he sets off in this direction, his space axis becomes distorted. Okay? Now let's take a look at that distortion. If he's traveling at half the speed of light, which means I went up 2 and over 1, what does his space axis look like? You take the reciprocal of that slope, which is up 2 over 1. So you flip it, and you put 1 over 2. And now I will draw that in at 4 minutes so you can see what it looks like. So his space axis looks like this at 4 minutes in. Okay. Now what we tend to call these space axes, okay, these are called now slices. Okay. These are all events happening now. So everything along this line is the same thing that happened now, according to this blue guy. In 4 minutes, this green guy says, these are all events happening now. All of these events happen now. So when you tell him, all right, look ahead at 4 minutes exactly, now, 4 minutes, how far away is the leading edge of that beam of light? He would say, 1, he'd count along his space axis, 1, 2, 3, 4. He'd say, oh, that beam of light is 4 minutes away, 4 light minutes away. Look back behind you, Mr. Green Pants, and say, tell me how far away the beam of light is that's the other direction. 1, 2, 3, 4. 4 minutes. It works. So you combine Maxwell's idea that no matter what happens, you must measure light to be the same, and you filter in now Einstein saying you can distort time, okay? And you end up with this weird space-time diagram that means, so here's the implications of this, right? Let me go one more page here. Hang with me. I know it's been 16 minutes, but this is all we have this week. So let me go one more page here. And then let's take this. Here's my now slice for some stationary objects. And let's take a planet here. Let's call this planet A. And let's call this planet B. Okay? And those planets aren't going to move for our story. They're just going to stay there. Okay? So I'll draw lines up for planet A and planet B. Okay? Now, I'm going to have a set of twins. This is the classic twin paradox. And I'm going to call twin A, and I'm going to say, twin A, you're going to be red, if you can even see the colors coming through the paper. Twin A, you're going to stay on this planet, stationary. So I'll draw him right along the edge of the planet, stationary. Okay? And since he doesn't move, here is his space axis the whole way up, undistorted, no movement. Okay? Let's take twin B, and let's do twin B in, how about like purple? Well, that's pretty close to red. How about like this light blue? I'll go, okay, this blue's good. Now let's have twin B travel at, what do you want? How about 3/4 the speed of light? So blue twin is going to travel at 3/4 the speed of light toward planet B. So what this means is I'm going to go 3 over 4. 1, 2, 3, 4. And there is my path of this twin traveling to this planet. Okay? And the moment, Einstein says the moment he sets off, his space axis automatically distorts, okay, by the reciprocal of 3/4. So it would be 4 over 3. Okay, so let me draw that in A. You probably won't even see the difference, but I'll do it in a little darker blue. 1, 2, 3, 4, 1, 2, 3. 1, 2, 3, 4, 1, 2, 3. Okay. So this is what his space axis looks like, and this is kind of freaky if you actually think about the implications here. So what I'm about to draw in here is all events that happen at the moment he left according to him. Okay, this is his now slice. This is the moment he leaves. Leaves. This is the moment he leaves. Are you following me? The moment he leaves. This is the moment in time when he leaves. Okay? So when this is the moment he arrives. So I ask you, how much time did it take, if these are years, light years of distance, okay, and these are years of time, according to him, he left here. You could pick any moment on here and say that's a moment he left. That's the same exact moment as this moment. So he left here and he arrived there. So it took him 1, 2, 3.5 years to get there. What about the red twin? Remember, his space axis never distorts. So we know the moment he left is down here. According to him, the moment he arrives is right here. So you ask the red twin, and you'd say, how long did it take you to get there? Well, according to him, it took 1, 2, 3, 4, 5, 6, 7, 8. So literally, red twin is 8 years older when blue twin arrives, and blue twin is only 3.5 years older, because the distance between when you left and when you arrived has shrunk in space-time distortion. Now this has really weird implications, because what if there is a civil war on planet B right here? Okay? Civil war happens right here on planet B, in this moment in time and space. That's 2 years, according to Red, 2 years after he left. So Red, see, oh gosh, look at this. There's a civil war happening. Blue twin, be careful. There's a civil war happening. Blue twin looks at it and says, what are you talking about? The moment I left was 2.5 years after they had already finished their civil war. Okay? So the weird implications of this become someone's present, someone's now slice could be someone else's. This event doesn't happen. The moment he left doesn't happen for 5 years, according to Red. Someone's present is someone else's past, is someone else's future. There is no, when you say past, present, and future, that is all totally relative to you and your situation. There is no universal past, present, or future. Okay? And typically, hopefully this sank in as much as it sometimes does to kids in class when we talk about it. But it has a weird effect, like if my future is someone else's present right now, then how do I change that if it's already happening according to some species or something out there, right? So it has sort of this weird mind-boggling effect. So I know this was a 23.5-minute video, but I feel like it had to be done so you appreciate the implications of there is no such thing as past, present, and future. So if you hung with me, use this to answer the questions for level 1 and 2, and then there's a video that goes with level 3 and 4, and that is your assignments for Unit 9.